Okay, yesterday, but I hope to get across to you kinds of exponentials, the kind that's called exponential growth. And don't talk right now, please. Stay with me. All right, exponential growth goes like this. The graph goes up. And the bigger the base gets, like if I were to change this to a 12, something ridiculous like that, then it would get super steep. It would go like this. Whew, really, really steep. In fact, probably steeper than that. But anyway, then the other kind is exponential decay. And that's where this would be like a 1/2 x. Okay, and that would be, or not decay, like, again, a steeper one, if you had y equals like 1/8, that's really cutting a lot off each time. 1/8 as big as it was each time. That would be super deep decay. It would go like, whoa. Okay? Oh, there's growth and decay, and generally what the graphs look like. Are you good with those? Two. The third is 8. Can't argue with that. Go ahead. Okay. Don't think that way. You don't want to know how much steeper is it. You need to know that it's steeper, and that the bigger that it gets, or the bigger the denominator gets, the steeper it'll get. There's one thing that you should try to be able to piece together, though. Do you get half is the exact same thing as if I said 2 to the negative? That is 1. You get how for the negative 1 power puts 1 over something? And then do you get this 1/8 here is really 2 to the negative of what? 2 to the negative. Because 2 times 2 times 2 makes 8, right? And then the negative part makes it flip. So if you see this graph, y equals 1x running around, do you get that that's the exact same thing? These are the same thing as each other. Okay? So it might look, at first when you look at this, you might think, it's growth. It's growth. That turns it back into 1/2, and then it's really decay. All right? So if you saw that y equals then that'd be the exact same thing is if I do 4 to the 3rd power and put it to the x. What is 4 to the 3rd? 64. And then what's that do to it? 1 over like that. You get that that's the same thing. Is a super steep decline. It's like super fast decay. This one is the same exact thing. They're identical. It's really hard to like tell them apart. In fact, you could really screw this up easily. All right. So now, let's talk about E. If I said, what's pi? You'd say 3.14, right? What's E? Nope. When you see an E on your calculator, I know you're thinking that the calculator says E to the whatever, it means times 10 to the whatever. It's not it. E is a number. Just like pi is 3.14, E is a number. All right, since you don't know it, write it at the top of your paper. This is a really important one. E is 1/8. Yes, it's just like pi, 3.14. It goes on forever. Pi goes on forever. This goes on forever, too. E goes on forever, but the beginning of it is 2.718. So we introduced this new function, but it's the same thing. If I had said 2 to the x, you should be like, oh yeah, I know what that is. It's exponential growth. And it kind of looks like this. And it goes up. It goes right there at x0. And then this one, though, is since E is 2.718, when I go like this, y equals, don't freak out like it's an all new function. It's not. It's just 2.718 to the x. Get what I'm saying? So it's just exponential growth again, and it's just steeper than the other one. So if I was going to do it with the other one, was kind of looking like this, maybe I'll just make it more steep this time, and I'll say like that. All right? Okay. So this graph right here is pretty much the same as what we did yesterday. All right. And it's a good thing that that's simple because there's a lot more to learn than just that. Yes? Good question. It's not like in pi we always use it with circles and stuff that E you always use in, but E is used a lot in this. Do you remember log base 10? Common kind of a log, and you can do that with a calculator. You just type in log 5 because it assumes base 10. There is a base E called the natural log, and log base E is ln. There's an ln button on your calculator. That's where we're going with this. That's why we're talking about E today, is because you're going to use log base E, which is the same as ln. Okay, so I don't expect you to be an expert on E. I don't expect you to derive where E comes from. It's just E is a number. That's the main thing I want to get across to you. It's about 2.7. Yes? Yep. Like these. Oh, so if you double reverse it, you say y equals 1/2, but then you put it to the negative second power. We aren't going to do that to you, but if we did, you'd have to process through what is right here that's being put to the x. And that would be square it, and then flip it, makes it 4. That would be the idea of 4 to the x. So yeah, all of a sudden it's growth. Get it down to a simple one. Picture what it looks like, and that just looks like the 2 to the x except steeper. All right. So now, let's talk about yesterday's main thing. The main thing you needed to know from yesterday. Y equals a. I'd give you 2 points, and you'd stick them in, and you'd figure out the equation. I'm going to do one in super speed version. I'd say, okay, let's see. Here's a picture. Here's the starting value at 0, 2. And then let's say another point at 3, 10. Then I would say I'm going to put in my starting value here. This one goes in for x and y. Would end up pushing them, please. And put in the x and the y. Here I'd 0. And then I have 2 equals a, b to the 0, and b to the 0 thing because it turns into 1. And so then I just know that a is 2. It's 2 equals a times 1, which is a. It's 2. Now, couldn't I just stuck a 2 in there? Sometimes that'll burn you. I'm warning you. That's why I keep doing it this other way. All right, so... sorry, the alignment's off on my board, so I screwed up my picture. There it is. Okay. So, now that I know a is 2, I'm going to go y equals 2b to the x, and then I'm 10 equals 2 times 3. No, b isn't 3. X is 3. And then I divide by 2 on both sides. 5 equals b to the x, and then I undo that somehow. How do I get the x? Wait a minute. That's 3. 3. That 3 off of there. Cube root, good. Put this to the 1/3 power, and the b is alone. And now I'd have 5 to the 1/3 power. We're going to give you numbers that'll work for like 8. If we add 8 to the, or you should be able to say, oh. All right. So there's the basics of it, and now I've figured out what a and b are, and my final answer would look like b with 1.863 or something. Units to the x. That's what you're looking for, is an equation where you know what a and b are. You have one on your worksheet to review, but because I know this is an important topic, we typically test on this kind of thing. We've always done it where we give you 2 points, and you have to use that one equation to figure out the equation of the line. We've done it with parabolas, and now we're probably going to do it again with these exponentials. So here is a picture. If 0, comma 5, and this is 3, comma, make it 2 square root. That's 2, let me think, 10. Would you please figure out what the equation for that would be? Start with y equals ab to the x. Put the calculators away. You can't use them on this worksheet anyways. And again, start with the starting value. Makes sense. What you should have done is started with this point and stuck it in here and here, and you would figure out that x, then this is 0 and this is 5 equals a b to the 0, and yay, that part. So yes, you can usually assume, but usually is a scary word because it doesn't always work then. I would always start with that process, because what if they throw in some other number here like -6? Then your number wouldn't just be a. You can't just say a is 5 for sure until you've checked. All right, so okay, let me go back a couple pages. There it is. So now, if a is 5, then I have y equals 5b to the x, and in this, and I put in x is 2 and y is 10, and I equals 5b to the second, divide by 5 on both sides, 2 equals b to the second, and I have to take the square root of both sides, and I have the square root of 2, which is the square root of 2. So I have b is the square root of 2. Now, typically I need a plus, but for that on a graph like this, I'm only looking for, I don't need, because I know I'm in the here. So final answer, square root of 2. Now, what is the, well, actually, it's not the final answer. The final answer is to write the whole equation out. Y equals a, b, which is x, which is right there. All right, now that would also be the same as square root of 2. You get, you could write as 2 to the 1/2 power to the x. So then I could really write it as this, times 2 to the 1/2 x, or 2 over x. Well, that's a little bit of a stretch, but you didn't have to do it that way. You could have left it this way and meant just fine. Raise your hand if you had that one right. Okay, good. Now that's the main stuff from yesterday, and again, what I've introduced now for today is that potential that you could have an e thrown into your problem, and all that means is e is about 2.7-ish. All right, now let's talk about the next major topic, which is comparing exponentials. If I have the x and have, which one's bigger? Well, it's kind of hard. Depends on what you mean by bigger. In some parts of the graph, one of them is bigger, and on the other parts of the graph, the other one's bigger. Well, how do you tell where one thing's higher on the graphs? I'm going to graph both of these. I'm going to do this 9 to the x, what it would look like. Here's my axes. My 9 to the x is going to be super steep. It's going to be that. Okay, compare that to the 4 to the x, which I'll leave in red, and that's going to be more like. Now, which one's bigger than which one? Well, it depends on where you look. On the right side of the graph, the blue one's bigger because it's higher. On the left side of the graph, the red one's bigger because it's higher. So where does the break point? The break point is right there, and they both always are going to go through the point 0, comma y, because when x is 0, see how they turn into 1s? Because anything to the 0 power is equal to 1. All right, so now, if the question was, where is 9 to the x bigger than to the x? I would say it's where x is what? Greater than 0, because from here on, the blue one's taller than the. It is, if you look at the, all I can tell you is if you look at the graph, it's going to be taller. It's going to be higher. I guess another way to say it is if you actually put the numbers in, we're putting in a negative for x, it kind of reverses things. Okay. All right. So now x is bigger than 0, but my answer for this, because that's the part of the graph where the blue one is higher than the red one. From here over that way. Okay. I'm going to give you another one. I want you to lunchtime. I think you can go to lunch. Catch you after lunch. We're back from lunch and we're recording again. We have a lot to learn really fast. That's one of the problems with Precalc is you got to remember everything from last year and then you build on it. Well, I got to remind you of what you learned in the course of a week in the next 10 minutes. All right, so let me show you how you did base change problems last year. And this is going to come up again today. If you had 2 to the 2x equals 4, you could solve that if the bases were only the same. Because if you could have a situation where it's like 5 to the x equals 5 to the third, well then of course x would have to equal 3. If the bases are the same, then these have to equal each other. Alright, so back to this problem. If I had this equals 4, then I can replace the 4 with, and now they have the same base. And if they have the same base, I can, it's not really canceling the bases, but what I can do is set this must equal that. 2x has to equal 2, and therefore x would have to equal 1. Do you remember base changes like that? All right, here's another one that's a little more complicated. Let's say that device goes on my desk. There. Thank you. 9 to the 2x equals 3 to the fourth, let's say. That's not on my desk yet. Put it there and put it later. Well, we can explain that. All right. So if I'm right now going to take these guys and make them be the same, I got to replace the 9 with something. What could I do? I could replace the 9 with 3 to the something has to equal 9. What is 9? 3 to the second. See, I'm just replacing the 9 with a 3 to the second. See, this side doesn't change at all, and this 2x needs to come down and be right here. So all I did was replace this part right here with 3 squared. Now, when the bases are the same like they are, see, this is the same as this, then that means this has to equal this. And notice you have to distribute this out. 2 times the 2x makes 4x equals 4. Okay, so 4x equals 4, and once again, x equals 1. And they don't always come out that way, but that's a couple times in a row here. I want you to try one. You need to know this for a big section of your homework today. Let's make it 144 to the x is equal to 12 to the third. All right. They have the same base each other? Yeah, Ken. How can you rewrite the 144 as what to the what? This 144 right here. That's 12 squared to the x equals 12 to the third. Now how do you get all the bases the same? And therefore, this has to equal this. And that's 2 times the x because of the way the exponents work. When you have power to a power, you multiply them. 2 times x is 2x equals 3. And so then the final answer is x equals 3 halves. So really, if I put the 3 halves right here, that's how I could check and see if it actually works. And 144 to the 3 halves, if you actually multiplied it all out, it would equal 12 to the third. All right, let me give you one more like that. Make sure you get this. 4 to the 2x minus 3 is equal to 2 to the x plus 1. That's a tricky one, but the same basic process applies. We need to have them both be base of 2. So I'm going to replace this 4 right here. I'm just going to erase it because I can. And I can put a 4. Now the base is the same, right? So your final answer ends up being a little equation. And you just have to solve the little equation and you get it. Now one mistake right here. Do 4x minus 3. That's not 4x minus 3. It's what? 4x minus 6. You got to distribute that too. 4x minus is equal to x plus 1. Now I have x's on both sides. Get rid of the smaller one. And I got 3x minus 6 equals 1. And then I'm going to add 6 to both sides. 3x equals 7. X equals 7/3. Did I screw something up? I heard a voice. I think I did it right. Okay. All right. So moral of the story. Get common bases. Once these bases are the same, then the exponents will have to equal each other. All right. There's a big section on there on that. Now, there is more to learn, and to be honest, I felt like today was just a little bit too much, and so I am not doing the last part until tomorrow. So I'm only assigning, that's plenty to know for one day. We're doing 1 through 15, and I'll start it with you and do probably 4 or 5 of those with you right now. So I'm going to pause for a second while I hand this out. Back with you, number 1 on the worksheet says, oh, look, it's got 2 points. It's got 2 points, and it's got a request for what's the equation for this. So what you do is you write y equals a b to the x. First you stick in the starting value, which goes here and here, and you'll probably figure out what a is. And then once you got a figured out, you stick in the point here and here. We've already done it times. This is a review. I don't want to do that one for you. I want to move on and do problem 2 with you. You can finish 1 later. Okay, so number 2. It says, describe how to transform the one graph into the other, and then sketch them. I encourage you to sketch them first, and then you'll have a better time changing the one to the other. It says f of x is equal to e to the x. Ooh, scary. E. It's just 2.7. It's exactly, if you want to just write 2.7 to the x, it's the same thing. Rounding it. The other one is g of x. I'll write that in a different color here. G of x is equal to e to the negative 2x. There's a negative in the power. That really means that it's decay. Okay? But back to taking a look at these 2 graphs. If you just sketch the black one here, the 2.7 to the x, it just looks kind of like this. There, the parent one. And then what change did I make? Well, I put it to the negative 2nd, which does 2 things to the graph. It's going to make it flip. You remember which way flip? It's on the inside, which is horizontally. Left, right is another way to say it. It's going to flip left, right, so I'm going to start going down like this. Notice it's turning into decay. And then the 2 part is it's getting scrunched. It's not twice as wide because the stuff on the inside is counterintuitive. It's half as wide, so it's going to take this one and scrunch it in. I don't know if I can. Yeah, that's kind of scrunching it. There. Now, how do you do that? I don't know. You're just going to take the number, the width in half. And so the thing gets to be smaller and smaller. Anyway, bottom line is you've got your graph, and it generally looks like that. Here's the parent one. Here's the new one. Now, what changes did you make? Well, they wanted you to make a list, and you did a reflection over the... Over which axis did we go over? Over the y. And the second thing we did was a scrunch. There's a more official name for that. Horizontal shrink. Very good. And that. Horizontal shrink. Okay. And problems 3, 4, and 5 are going to be the same kind of deal. You're going to start by graphing the parent one, and then you're going to stretch it and move it and flip it and that kind of stuff. All right. Those will be easy. Number 6 and 7. Number 6. At first glance, you might think that that is growth. It says, is it growth or decay? And you're going to look at it, and you're going to think, oh, it's growth because the base is... But it's not, because it's got a negative power, which makes the thing... which makes it turn into decay. So if I were you, it's going to ask you to graph it anyway. No, it actually doesn't require you to graph it, but let me tell you, it's way easier if you do. So I'm going to make a quick sketch of it because I have to do the limits for this, and to have the picture is priceless. All right, here's the parent one. That's parent for exponentials. It's like 3 to the x. And then I have to flip it and scrunch it, and so it's going to look something like that. It's squished narrower, and it's been flipped left-right. Okay, so now I'm getting rid of that one. Toss it off to the side. It's this green one. So what am I supposed to do? To state whether it's growth or decay. Just look at it. Does it look like it's growing as you go from left to right? No, it's decay. So you say decay. And the second thing is use limits to describe the end behavior. I could definitely see that coming up on the next test because they're going to want to bring back limits. In case you've forgotten how you write a limit, it's really easy actually. It always looks like this. Limit of the function as x approaches whatever. It usually approaches infinity or negative infinity, but I don't need that yet. There, that's how you always write a limit. And then the only question is what you put here and what you put there. Okay? So now, how do you write the limit for the left side? Left side is way over there. What is x approaching? If I go way negative infinity, good. And it then becomes the y value is right here, and what's the y value when I get way over here? What's y going to be? Way up there, which is what? Infinity. So there's my left limit, my left end limit. My right limit starts exactly the same way. Lim of the function as x approaches whatever, and this is the right side now. So if I go way over here, it's going to be x approaching positive infinity. And when I get there, what's the y going to be? You are right. 0. Okay. You're right. But the limit means if I, just like I'll never get to infinity, it's like if you could get it to infinity, it's the limit, means it approaches. Technically, it never gets to 0. It approaches. Gets closer and closer and never touches 0. Okay, moving on to problems like 8 and 9. Look at number, oh wait, that's the same kind, forget that. In the same directions, so we'll move on to 10. Number 10. It's asking you to solve it graphically. That means graph. Alright, so I got to graph 9 to the x, and I got to graph 4 to the x, and to kind of see where they cross, but that's not the whole story. If you were finding what it was equal to, then you'd just graph both sides and see where they cross. But what I'm doing is finding out where the one is less than the other. I need to graph them, and I do need to see where they cross. But then I got to figure out wherever this one is smaller than that one means under it. So I'm going to graph them both. I'm going to graph this one in blue, and that's going to just be a really steep one. And I'm going to graph this one in red. 4 to the x is going to be not as steep, so it goes like that. Now, way over there on the right side, the blue one is bigger than the other one. But all I really wanted to know is when is the blue one less than the red one? And it's when the blue one is less is when the blue one is under it, and it's in this zone right there. And what I'm asking, the only variable in the equation is an x. So it's about, how do I describe this using x? I say it's when x is less than 0. You're right. Okay, that's how you do couple different and see where they cross. And then only other ones I'm assigning are 14 and 15. And on these two, we have to use that common basis thing that I told you about. So let's put number 14 together. It's got 3 equations, y1, y2, and y3. I need to write them, so I need somebody to read them. What's to the power of 2x plus 4. Okay. And then what's y2? Like this, okay? And what's y3? To the power of? All right. 2 of these are equal. One of them is not at all like the others. Can you tell right off the bat, just looking at them, which of these is not like the others? y1, y2, or y3? y2. I'm ruling out y2. I think y1 and y3 are the 2 that are alike, because this one's got a shift involved. These don't have. Okay, so now how do I prove that y1 and y3 are really equal to each other? You can't just say y1 and y3. You'd have to. How do you prove it? You'd say 3 to the 2x plus 4 is equal to 9 to the x plus 2. And if you want to prove something, You leave one side of the equation alone, and you work with the other side in equals. That first one, okay? So in other words, I got to either mess with this side and turn it into that, or I got to mess with the other side. I agree. We should mess with the other side because, you know, we just practiced this. What are you going to do with this side? You're going to take that 9, you take it out, and put 3 squared. Instead of that 9, you're going to put in 3 squared. And why is that good? Because now this side, when you multiply it all out, is going to turn into that. How do you show your work for that? I guess I've done the work so far. Remember, leave the left side alone. You just take this side, keep multiplying it all the way out, and equal. Sorry, take the right side and multiply it all the way out, and eventually it'll equal the left side. So leave this side. Whenever you're proving something, leave one side alone, and the other side, you keep manipulating until it equals the other side. So final answer here really comes down to this. That has to equal that, and when I multiply this out, it will equal that. So yay. The right side will turn into the left side. All right, same idea on number 50. A bit harder, but you can each of the two you think are equal, set them equal, do the base, and figure it out. All right, I am not going to delve into 21 until tomorrow. 21 is just a review, but I just didn't want to leave you one more thing to learn that felt like too much. So we'll talk about that at the beginning of tomorrow. All right, so your assignments 1 through 15, I've done several of them for you. No excuse why you can't. Remember, your retakes this time depend on you getting your homework done. Doesn't